Hello everybody, my name is Abtin Baghdadi. I'm working in the Institute of Structural Design, ETE, supervised by Mr. Professor Harald Kloft from Technische Universität Braunschweig. Here in this presentation, I'm going to talk briefly about the performance of Heinz Isler shells under the seismic load on behalf of Professor Mahmoud Heristchian and Professor Harald Kloft. Generally, Isler found the form by the traditional methods by hanging the flexible elements which finds the form under the gravity and then rotating those elements to perform instead of tension now under compression optimally. So that's the traditional method that he mainly used in finding the forms, and he also had some minimum calculation which estimates the amount of the forces in his shells. But basically, he mainly followed his special and unique skills for finding the forms, not based on the calculation. Therefore, after him, different researchers tried to evaluate the performance of those shells under gravity, and we also, I'm in the same group of the writer, Mr. Heristchian, Mr. Kloft, and I also evaluated those shells under gravity regarding different components such as amount of the forces, deformation, fulminances, stresses, and also the geometrical differences between these shells. But not anybody else up to now has never evaluated the performance of his shells under the seismic load. The question is that, are these optimum shells able to resist against seismic load as well or not? So that's what we are going to evaluate and discuss in this paper. For that, we remodeled the shells and we referred to lots of references, and we selected the properties, geometries, and so on. We developed a special method for finding their forms and remodeling them, which was discussed in another paper. And we also used the SAP and Abacus as the main software to work parallel with each other and to compare the results with each other. As here we can see, these shells were selected. We selected them because they were used by him more frequently, and they were made by three different methods that Isler generally used for developing those geometries to be able to compare them with each other. For the evaluation, we refer to FEMA and ATC, and based on the rules the standard rules, we have to fit a bilinear curve to each pushover diagram to be able to discuss about the criteria. As FEMA needs, we have to find those bilinear diagrams in a way in which the amount of the area under the diagram are similar to the pushover diagrams, and also they cut the height of the diagram in something around 60% of the height, and so on. For that, I assigned and I developed a specific unique function for each pushover diagram to be able to find these bilinear elements. So up to now, in addition to evaluating the evaluating the shells under pushover analysis, we also have some functions which would be later referred to and addressed again, which is related to each pushover diagrams. These are really precise and fitted by MATLAB in a really good method. And up to now, we have those curvatures and the result of the pushover. The main result is the response factor, which can be later used by the other designer to develop and to reanalyze those shells and remake and rebuild them based on their local place criteria and their specific country's seismic standard. So we have those response factor, and people can refer to in addition to some other data that we mentioned in the paper. The other point is about the hysteresis analysis. The red line shows the pushover and the dotted diagram shows the hysteresis analysis. These shells have different performance. Some of them need really high amount of the energy for collapsing, like garden shell, and some geometries like Northridge, Natur Theater shell would face a really premature buckling. And generally, I can say even these shells may have a different performance in two sides of same direction, like this Nature Theater shell, which shows two different performance in two parallel directions, and the other details were discussed in the paper, which can be referred. And the other evaluation, which is related to hysteresis, is discussing is assigning the deformation on top center of each shell and recording the amount of the shear in the support part. That's similar to pushover, but based on the spectrum that we applied the deformation on top center, and we applied the deformation on each shell. The point is, the result of that can be seen in these blue diagrams. But if we put the time as the variables in the fitted curvature to the pushover diagrams, we also can quickly, instead of that much time-consuming analysis, we can find the similar performance shown in the red dashed diagrams. So the fitted pushover diagrams regarding the amount of the time as the variables can show similar performance to the hysteresis analysis quickly. Here we can see amount of the time in which the first hinges was faced by each shell. And generally, I can say, unfortunately, these geometries cannot resist against the seismic load that much. And as a solution, we found the best method is using the base isolator, as I put that, and we can see that how these technique and base isolator, which was developed based on the Mechanogumba, can reduce the amount of shear in those shells to be remade in the places with a probability of seismic or an earthquake load. Thanks a lot for your attention.